Okay, now we're going to discuss the multiplication algorithm. That is the procedure for multiplying two numbers together. As we've discussed with our other algorithms, what you do not want to do as a teacher is just list steps of an algorithm without any understanding behind them. So imagine what would happen if you did that with multiplication. 38 times 6, let's take as an example. Now, we know as instructors that the proper procedure here is to multiply 8 times 6, and we get 48 if we do so, and put the ones digit down in the ones place of our answer, and the tens digit we put above the tens digit of our first factor, 38. Now, that's a relatively straightforward step, but the next step is a seemingly arbitrary one if we don't have any explanation to go along with it. The next step is we multiply, so the correct step is to multiply 3 times 6 and then add 4. But if we don't have any understanding behind this, it is certainly conceivable that a student can mix up those steps. A student might be thinking, well, maybe I know that I multiply 2 of these numbers and I add the other one, but they might forget which is which, so they might very easily multiply 4 and 3 and add 6. So incorrect is really any other sequence of multiplying 2 numbers and adding. So for example, 4 times 3 plus 6, we might add the 6 and the 3 and then multiply 4, and so on and so forth. There are any number, well, there's a large number of incorrect ways that if we have 3 numbers, we can multiply 2 of them and add another one. Okay? But if we are just told the steps in a procedure, it is certainly conceivable that a student can make that mistake. So as we did with addition and subtraction, what we want to do is we want to justify every single step on the multiplication algorithm. Why are we doing what we're doing? And this is going to be done in a couple of stages. The first stage is going to involve multiplication by a single digit number, and preferably a relatively small single digit number because we are going to use chip models. And we are going to have a slight variation on our chip model in that we are going to combine a chip model with a rectangular array. Because remember from our previous discussion of multiplication, we can think of 32 times 3 as 3 rows of 32. So we can just draw this on a chip model. We can just draw 3 rows of 32. 32 is 3 tens and 2 ones, so we can simply draw 3 rows of 3 tens and 2 ones. Okay. Now again, this is a pretty straightforward example because it does not involve regrouping, but what it does show us is the key kind of features behind the multiplication algorithm. And really the key feature is the distributive property. It's very clear from this model that to solve 32 times 3, we are multiplying 30 times 3, and we are multiplying 2 times 3. Right? And that's what we're going to be doing in general when we multiply 2 numbers together on the algorithm. So we also see how this is going to stack up in the form of the algorithm when we just line the numbers up and multiply them. That we multiply clearly on the algorithm, we multiply 3 times 2, and that's where 6 comes from in the ones place. That's how many ones we have. And another way of looking at this is then we multiply, this 3 is in the tens place, so it really means 30. We're multiplying 30 times 3, and 30 times 3 is 90. And that's where our 96 comes from. Now, oftentimes students are not actually taught these exact steps. They're taught to combine these 2 steps in one step to make things a little bit more efficient. But it might be worth your while as an instructor, maybe the first couple of times to illustrate this, to actually show all of these steps to really get the distributive make the distributive property clear. Now, again, this is an easier type of problem. The next level up from this is a problem that involves rebundling. Okay. So maybe let's do one of those. So for example, let's say we would like to multiply 36 times 4. Again, notice that as an instructor, if you were teaching this process to a class of students, you would probably start with several chip models before you showed the actual algorithm. I'm doing them in tandem so I can show, again, how one step on the model corresponds to a step on the algorithm. So using our rectangular array interpretation or model of multiplication, we are going to interpret 36 times 4 as 4 rows of 36. Now, the reason I need a hundreds place is because I know that my answer is actually going to be a 3-digit number. Okay? But again, at the start, if we want to illustrate 4 times 36, we just have 4 rows of 36. 36 is 3 tens and 6 ones. So I simply draw 3 tens, or excuse me, 4 rows of 3 tens and 6 ones. Now, much like the addition and the subtraction algorithms, now all I do is solve the problem using place value on the model and then relay those steps to the actual algorithm. Okay? So our first step on the model would be to use our rule of base 10. Recall our rule of base 10 is that 10 of any one denomination is equivalent to 1 of the next higher denomination. We have a lot of 1s here, so we can group 10 of them at a time and translate them, or convert them, I should say, to 110. So we have 10 ones becoming 110, and we have another 10 ones becoming 110. So this would be our first step of this process on the model. And then what we want to do to teach the algorithm is just translate that step from the model to the algorithm. What did we actually do? We could do this process without circling chips. We can do this just with arithmetic. What we did was we clearly took our original 6 ones and multiplied by 4. So that's what we're going to do over here. We're going to multiply 6 times 4 to get 24 ones. But from our rule of base 10, we know that we can take 20 of those ones and convert those to 2 tens. This is why a 2 is placed here and a 4 goes in the ones place of our answer. Because if we started with 24 ones, 20 of those are going to be taken, converted to 2 tens, and we are left with 4 ones. Now, we simply, on the model, keep doing this until we're finished. And we see in the tens place that, again, we have at least 10 tens, and we can take 10 of those tens and convert those to 1 100. So there we have 10 tens equaling 1 100. Now the question is, what did we do on the model? Can we translate that over on the algorithm? So now that step that seemed a little bit arbitrary at the beginning of our discussion, if we didn't have any understanding behind the algorithm, is an obvious step. What did we do on the model? We took the original 3 tens we had and multiplied by 4, but then we had to add in the additional 2 tens we got from converting our 21s. That's the reason why, at this stage, we multiply 4 times 3 and we add 2. So there's a reason why we do all this. Again, with all of the arithmetic algorithms, every single mark we make on the algorithm needs to have a reason behind it. This is the reason that we multiply 4 times 3 and add 2. It seems arbitrary on the surface, but if we draw a model, it seems perfectly reasonable. So that's where we get our 14, or I should say our 4 tens and then 1 100. So a 4 goes in the tens place of our answer, a 1 is in the hundreds place of our answer, and there we have it. So even though we have only illustrated multiplication by a 1-digit number, all of the key features of the multiplication algorithm have been shown. We've illustrated the distributive property, and we've also illustrated rebundling. Now, the next stage is moving on the algorithm to multiplication by 2- and 3-digit numbers. Now again, clearly we are not going to be drawing chip models for these problems, because we would be drawing chips all day long. So for example, if we wanted to multiply 32 times 24, again, this would translate to 24 rows of 32, which we are certainly never going to draw, okay? But it's going to turn out, if we use the distributive property and expanded form, place value notions, then we can use just the ideas that we illustrated with 1-digit multiplication to solve really any multiplication problem. So we want to think of 32 times 24 as 32 times 20 plus 4. So we're going to use expanded form on 24 to write it as 20 plus 4. And now we have the distributive property. 32 times the quantity 20 plus 4 is equivalent to 32 times 20 plus 32 times 4. The good news is, we already know how to handle 32 times 4, right? This is simply a multiplication by a 1-digit number, which we already know how to do. Okay? Now, 32 times 20 might seem on the surface like multiplication by a 2-digit number, but really it isn't if we use place value. 32 times 20 can be thought of as 32 times 2 times 10. Just using the associative property of multiplication. We can think of 20 as 2 times 10, and then we can simply group together the 2 with the 32. Since we already know how to multiply by 10, it just involves a place value shift of one place, then really, if we know the answer to 32 times 2, we really know the answer to 32 times 10, right? And since 32 times 2 is equal to 64, 32 times 20 is equal to 640. And this is all there is to it. If we use expanded form in the distributive property and we already know how to multiply by 1-digit numbers, we put all that together and that allows us to multiply by any number we like. So 32 times 24 is simply seen as 32 times 4, which is 128. And then 32 times 20, which we just saw as 640. The distributive property tells us we add these numbers up, that's where our 768 comes from. Okay. Incidentally, if oftentimes when the multiplication algorithm is just taught as a procedure, we are just taught a series of steps to carry out, and oftentimes this 0 is either not put in at all, or a different symbol is put there, and that's really not a good way to teach the multiplication algorithm. It really misses the entire point of distributive property. So the distributive property makes it obvious that this number here is not, this 2 represents 20, right? So our next multiplication is not 32 times 2, it's 32 times 20, which is 640. Now, there's also a pictorial way to obtain these so-called partial products that arise in a multiplication problem. And this can be useful for students that are having a hard time seeing the distributive property written out so-called algebraically. We can use a rectangular array. 32 times 24. Again, we can think of as 24 rows of 32 objects. Draw a little bit better of a diagram here. Now, this is a lot of objects. We just saw that it's going to end up being 768 little squares. We certainly don't want to draw all these out. But what we want to do instead is we want to use our imagination a little bit. Imagine if we were to draw out 24 rows of 32 objects, how would we be able to count those objects? How would we be able to figure out how many objects there were? Well, one way of doing that is to imagine 24 rows broken up into 20 rows and 4 rows. Okay, again, I'll start drawing in some boxes. I'm certainly not going to draw them all in. So again, we might consider or try to imagine in our heads 24 rows of 32 boxes and think of the 24 rows being split up as 20 rows and then 4 rows. 20 rows plus 4 rows is certainly 24 total rows. And we might do the same with the number of columns. We might break up the 32 columns as 30 columns and then 2 columns. And if we do this and we do some clever subdividing, like so, we see that we can count the total number of little boxes in the entire array by counting the number of boxes in each of these 4 rectangles and adding those all up. So for example, in this upper left rectangle, we have 20 rows of 30 boxes, which we interpret as 20 times 30, which is simply 600. In this tall skinny one over here, we have 20 rows of 2 boxes, which we interpret as 20 times 2, or 40. In this flat rectangle down here, we have 4 rows of 30 boxes, which we interpret as 4 times 30, which is 120. And lastly, in this little box down in the corner, we have 4 rows of 2 boxes, which we interpret as 4 times 2, or 8. Now, if we were multiplying, recall, and since it's on the other board, let me just recall how we did this with the distributive property a second ago. Our partial products were 128 and 640. Now, on the array, you can see where that 128 and the 640 came from, right? The 128 comes from the 120 plus 8. There's our 128. The 640 comes from our 600 plus 40. There's our 640. So this rectangular array can give us a kind of a nice way to visually represent the partial products that occur in any multiplication problem.